is, faster than, and C. In C, introduction. A very common low-level performance interview question is faster than equal in C? At first, it seems like one operator should be simpler than the other. But in real systems, the answer is not what most beginners expect. This topic explains how C comparison operators work, what happens at CPU level, compiler optimizations, branching and instruction costs, assembly behavior, modern CPU pipelining, branch prediction, benchmark reality, misconceptions, performance conclusions. This is a core systems plus low-level performance concept. Short answer: no. Question is not meaningfully faster than X question in modern C programs. In most real cases, check, they compile to identical or nearly identical machine code. Performance difference is 0 in practice. What happens in C code? Example: if X equals Y, do something, versus if X equals Y, do something. Both look different at source level, but compilers don't treat them differently in performance-critical terms. What the compiler does. Modern compilers, GCC, Clang, MSVC, convert both into a single CPU comparison instruction. Example: conceptual assembly. CMP X Y JL label. Jump if less 4 equals 0. CMP XY JLE label. Jump if less or equal. Key insight. Both instructions. Currents are single CPU compare operations. Currents execute in one cycle typically. Currents differ only in branch condition, not cost. So, X means JL, jump if less. LE means JLE, jump if less or equal. Same performance class. CPU level reality. Modern CPUs execute comparisons in ALU. Pipeline instructions execute condition checks in parallel. So the cost difference between less than and less than is effectively 0, what actually costs time. The real performance cost is not the operator. It is 1. Branching if X is less than Y may cause a branch instruction. 2. Branch misprediction. If CPU guesses wrong, no pipeline flush. Performance penalty, 10 to 20 plus cycles. 3. Memory access, much slower than comparison. Cache miss, cache, RAM access. Comparison cost breakdown. Operation cost, less than or equal. Negligible CPU comparison. Negligible branch prediction hit. Fast branch misprediction, expensive. Operator choice is not the bottleneck. Compiler optimization example. With optimization flags. GCC-02 test.c. Both. If X is less than Y, if X is equal to Y, often generate identical assembly structure. Benchmark reality. If you try to benchmark greater than or equal to less than, Curson results are noise. Differences disappear under optimization. CPU variability dominates. Any measured difference is usually measurement error, cache effects, compiler differences. Why people think is faster. This is a misconception because check feels simpler. Check fewer symbols in code. Check assumption that fewer checks equals faster. But CPUs don't execute symbols. They execute instructions. When differences might exist. Rare cases. In extremely low-level scenarios. Micro-architectural quirks, unoptimized code, -0. Unusual compilers, embedded systems with very limited CPUs. Even then, differences are negligible in real applications. Assembly-level insight. Condition A-B means check if A minus B equals 0 equals A. Means check if A minus B equals 0. Same arithmetic operation, different condition flag check. Branch-free code. Important insight. Modern high-performance code often avoids branches entirely. Example: int result equals X greater than Y, 10, or using conditional moves. Avoids branch misprediction. Faster than worrying about less versus less. Real performance bottleneck example. Slower code. For int I equals 0, I equals n, I++. Bottleneck. Access branch prediction, not the negative operator. Best practices. This. Focus on algorithm complexity, O log n. Optimize memory access patterns. Reduce branching where possible. Trust compiler optimizations. Common interview trap. If asked, is faster than equals best answer. Cuck. No meaningful difference. Cuck. Both compile to similar instructions. Performance depends on branching and CPU behavior, not operator choice. Simple definition. Both and X less in C. Compile to nearly identical CPU comparison instructions with no meaningful performance difference. Final summary. Is not faster than equals in practice. Compilers optimize them into similar machine code. CPU cost is identical or negligible. Real performance depends on branches and memory access. Key idea. Operator choice does not matter. Algorithm and memory access matter.